So in this video, we're going to be talking about graphing economic theories. Okay, so in the previous video, we talked about graphing economic data. All right, so when we're graphing economic data, usually we have what are called discrete points. All right, so we have a given set of observations. We have observation 1, 2, 3, 4, etc. And then we want to find a way of representing all of those points on a graph. Okay, and these points of data were presumably obtained by an economist actually going out into the real world and finding out what's actually true about it and then representing it visually. Okay, graphing economic theories is going to be a little bit different because it's going to be more mathematically abstract. Okay, usually we won't be dealing with discrete points of data, so individual points, but actually continuous data, so things like lines and curves. All right. Yeah, so there are several examples that I could think of useful applications of what we're going to go through in this video, which I won't necessarily go through in this video, except to illustrate the concepts. But needless to say, you really should master the content of this video before going on to study further chapters in your economics course, because chances are that when you start studying the different theories in the economic course, things like supply, demand, costs and production of firms, things like that, you're going to need to understand the kind of basic math, okay, that we're going to go through in this video. Now, this basic math is nothing but nothing but high school math, really. At different times in the video, I will flag where calculus could be used to obtain the same results, okay? But I'm not actually going to go through the calculus here because these videos are meant for an intro to economics course, and most intro courses don't require any knowledge of calculus at all, okay? If you want to see some calculus, because maybe you're in an intermediate or advanced course, you could always leave that in the comments down below, and I'll try to make a video in the future about it, all right? So on that note, like and subscribe and share these videos with your friends, colleagues, and classmates if you find them useful, and leave a comment down below, not only if you want to see some calculus, but if you have really any suggestions for future videos. All right, and I'll try to take them into account as much as I can. Okay, so let's start with a topic that we actually briefly talked about in a previous video, which is basically which are linear functions. Okay, so a linear function is any function that has a constant slope or a constant rate of change, okay? So linear functions have constant slope or rate of change, okay? And when you graph them, they look like straight lines, right? Okay, so you've seen many of these in the past. So let's draw one out and see what it might look like. So on our x-axis, you might have, say, I don't know, let's say consumption. Or expenditure. Let's say expenditure. Okay, so expenditure. So this is, right, dollars spent. Could be in a year, could be in a month, whatever. And then on this axis, you have, say, wage, right? Now, in theory, okay, expenditure might be thought or predicted to increase as wage increases. So you might represent this function by essentially a straight line, right? Something like that. Okay, now what is this straight line telling us? It's telling us that as wage increases, right, expenditure will also increase by the same amount for every comparable increase in wage. So if this is a +1, so for every increase in $1 of wages, expenditure increases by 50 cents, well, then that will be true for any $1 increase, no matter where you start. So if you take a $1 increase here, you will still get a 50-cent increase in expenditure. Always, okay? That will always be the case. Okay, so that's what we mean by constant rate of change, okay? Constant rate of change means that when you change your x variable by some amount, in this case we decided to say by 1, but it could be by 2 or 3 or 4, by the same amount, you will always get the same increase in y. Okay? That's why it's a straight line, that's why it's called linear, and that's why we say that it has a constant rate of change. Okay, now, slope. All right, how do we calculate the slope? Well, we're saying here that for every increase in $1 in wages, we get an increase in 50 cents in expenditure. Okay, so let's make that concrete and just put some numbers, okay, just for the sake of making it a little bit clearer on our graph. All right, so let's say that we have 2 points on the graph. Call these point A and point B, okay? Now, point A, our individual is making a wage of, and this will definitely not be drawn to scale, okay, but it's okay. This is just for the sake of an example. Our wage is 10, and at point B, our wage is 15. Okay, and we already said that for every dollar increase, okay, expenditure increases by 50 cents. So in this case, let's say that at $10 of wages, our consumer is spending is spending, well, okay, it'll depend on what exactly our y-intercept is. Okay, let's just say that this is 5 here. We'll get to that in a second, okay? So for every dollar increase, right, so for every dollar increase in wages, we said that our expenditure goes up by 50 cents, right? $0.5 increase in expenditure. So over here, we start at 5. So let's see. There's been a $10 increase. So that would be a $5 increase in expenditure. So, okay. So that works out quite nicely, actually. So we have 10 over here. And then we would have an increase of $5 in wages, right, from 10 to 15. So that would be an increase in $2.50 in expenditure. So we would have 12.5 here, something like that. Okay. Yeah. So okay. Now, so I'm just trying to make the example consistent with what we said with what we said before. Okay. So now, how do you calculate the slope? Because we already talked about rate of change. Rate of change was intuitively sort of understandable. Every time, as we said, wages increase by 1, you have a commensurate 50-cent increase in expenditure. Okay, so let's change that to sort of mathematical language and talk about slope now. All right, so, well, our formula for slope is delta y over delta x. Now, delta y, okay, so the Greek letter delta here, those are the triangles, okay? The Greek letter delta, just means change in, okay? So change in y divided by change in x, okay? So by dividing our change in y, so in this case, if we go from point A to point B, our change in y would be 2.5. There's been an increase in 2.5 of 2.5. So by dividing our increase in y by our, in this case, increase in x, so the increase would be an increase of 5, we essentially get, well, 0.5, okay, which is exactly what we expected. Our slope should be equal to our rate of change, right? So our rate of change was 50 cents per dollar, and we get the exact same thing back when we use our formula, okay, 0.5. So what is the equation of this line? Well, expenditure, I'll denote this by E, is equal to, okay, the y-intercept, so that's 5, plus 0.5 W, or wage, right? So this is the equation for this line. Now, how do we interpret this equation? Well, we want expenditure to be equal to 5 when wage is 0, right? That's what the y-intercept is. When wage is 0, expenditure is still 5. Okay, well, what happens if we take this equation here and make our wage variable equal to 0? Well, 0.5 times 0 is 0, plus 5 would just be equal to 5. So that's exactly what we want, right? And then we want this equation to be telling us that for every dollar increase in wages, our expenditure will go up by 50 cents. And that's exactly what we have, right? If this wage number goes up by 1, then our expenditure is going to be going up by 0.5 because you're multiplying wage by 0.5, right? So this equation tells us basically exactly what we wanted it to, which was essentially that when wages are 0, okay, expenditure is 5, and when wages go up by $1, then our expenditure goes up by 50 cents, okay? Okay, so that's about it for linear functions. But by the way, I want to just flag something super quickly, okay? When you're trying to find the slope, okay, it's very easy when you're just looking at a positively sloped line, so a line that goes upwards like this. Had our line been going downwards, so let's say we had a line that was downward sloping like this, okay, and we wanted to find the slope from point A to point B. Now let's say A was point, so by the way here, okay, this would be point, B would be point, whoops. Just for the sake of clarity of notation, point B here can also be denoted as 15, 12.5. Okay, 15 is the x-coordinate, 12.5 is the y-coordinate, and point A can be denoted as 10, 10. Okay, 10 being the x-coordinate, the other 10 being the y-coordinate. Okay, so I just wanted to make that clear if you didn't remember that from high school math. So with our downward sloping line here, let's say point A were something like, I don't know, let's say it were 0, 5, and then point B were 1, 2, right? So that would correspond to, let's say, this were so that would mean that this was 0 here on the x-axis, this here is the y-axis, this would be 5 up here, right? And then this would be 1 down here and 2 up there, right? Okay, now let's say we wanted to calculate the slope of this line. So we would want to do delta y over delta x. What I want you to be careful of is the sign here. Okay, so delta y, if you choose to start at point A, right, you're talking about a decrease of 3, right? You're going from 5 to 2, so that's a decrease of 3. Okay, so what you want to do is you want to start with your second point, okay? Your second point is 2. So you'd want to do something like 2 minus 5. And then do the same thing for your x coordinate. You start at 1, so 1 minus 0. And then you would get negative 3 over 1, which is equal to negative 3. The point is you want to have this negative sign, okay, because the curve is, the line rather, is downward sloping, okay? So just be careful of the signs. That's basically all I'm trying to say here, all right? I mean, you could also just very easily see that, okay, y is going downwards, right? So because y is going downwards and it's changing by 3, you could just write negative 3. And then x is changing by 1 because it's going from 0 to 1, but it's going upwards, so that's just 1. I mean, it's another way of putting it, or you could do the minus thing. Doesn't really matter. The point is, be careful of the signs. If the line is pointing upwards, you want your slope to be positive. If it's pointing downwards, you want your slope to be negative. Okay, so now let's move on to cases where the slope, the line rather, is not linear, okay, rather when we have a curve, okay. Now, this is one of those areas where I'm just going to flag that curves are kind of difficult to deal with if it were not for, without calculus, rather, okay. So I'm going to deal with this without calculus, but this is better dealt with calculus, okay? And you'll learn that in further courses if you continue in economics. All right, so I'm just going to name this graph generic y and x here. We don't really have to use any economic quantities. And let's say we have a graph with a curve. Oops. That looks like that. Okay, so this is clearly not a straight line. It's clearly a curve. Now over here we said that rate of change is equal to slope, right? So the slope just tells you that when we increase the x value by a certain amount, we increase the y value by a certain amount, or decrease it by a certain amount, right? That's what the slope is telling you. Well, we have a similar concept here, except the slope is not constant. The slope is changing, okay? A way of seeing this is to just see that the line is, or the curve is steeper here and less steep here, right? So this curve is decreasing by a greater amount here. Its rate of change is higher than it is here, or lower if you take signs into account, okay? So how do we determine what the rate of change or the slope is? Well, you would have to find the slope of the tangent line at a given point. So a tangent line is simply defined as a line that just touches this curve at a point. So let's say this were a straight line that just touched the curve at this point. That would be the tangent line. And if we could find the slope of that tangent line, then we could find the slope of the curve at this point. Okay, so let's call this point A. And let's say we knew 2 points on this tangent line. Let's say we knew point B and point C. Okay? So let's say this were 5 and this 10, and this were 2 and this 1. Well, now based on our delta y over delta x formula, we could find the slope of this tangent line, correct? So C is on the line, B is on the line, okay? That's nothing but what we saw earlier. It's a line with 2 points, right? B and C. A line with 2 points we could very, very easily find the slope of, okay? So let's do that. Let's find the slope of this tangent line. So slope of tangent line is equal to, okay, delta y, right? So there's a change in 1 here, but it's negative because it's going downwards, right? So we want to have a negative 1 in the top. That's our delta y. Over delta x. So that's our delta x. We have an increase of 5. Okay? So the slope of our tangent line is negative 1 over 5. And this is also the slope slash rate of change of the curve at point A. Okay? Now, economists have a kind of fancy word for this idea. This idea of the rate of change on a curve at a certain point, which is the marginal change. Okay? The marginal change in y at point A, given some change in x, is negative 1.5 in economics speak. All right? So what does this actually mean? Well, this is where it would be very, very helpful to have some calculus. Okay? What this means is that at point A, for a super, super, super tiny change in x, okay, y will be decreasing by negative 1 over 5. Okay? That's what that means. All right? So that's how you find the slope of a point on a curve. You have to find the slope of the tangent line at that point. All right? And if you have 2 points on that tangent line, all you have to do is treat it like a linear function and use delta y over delta x to find that slope. And once you have found the marginal change at that point on the curve. All right? Okay, so last thing for this video, we're going to talk about functions that have... by the way, I forgot to mention, marginal change can also be denoted as the marginal response of y. Okay, so in other words, a tiny, tiny change in x creates a marginal response of y of negative 1.5. These are all equivalent terms, okay? The important word here is really, really marginal. Okay, sorry, I just forgot to mention that. Okay, back to what we were saying. So the last topic of this video is going to be functions that have maximum points and minimum points, right? So let's just draw out an example here. So y, x, and let's draw a curve that looks, oops, that's pretty terrible. That looks like this. Okay. Now, this curve, let's assume, goes on forever in either direction, okay, in the x direction, but it clearly has a maximum here, okay? So this is the maximum. Now, what is the significance of the maximum? Well, the significance of the maximum is that, well, as you can see, the tangent line to that point. So remember what a tangent line is. The tangent line is a line that just touches a given point on the graph. If we drew the tangent line on this graph and we made it just touch the graph at point M, we would essentially get a straight horizontal line. Now, the slope of this line is 0. How do we know this? Well, because delta y is 0. There is no change in y from this point to this point, or from this point to this point, or from that point to this point. There is no change in y. Delta y, which is equal to 0, will be divided by some delta x, but no matter what, 0 divided by delta x is just 0. So the slope of that line is 0 at that point, which means that the marginal response of y is 0. Okay? And we could say the same thing about a function with a minimum. Okay? If we drew a function like this that sort of went on forever in those two directions, and we drew the tangent line to point small m as the minimum, we would essentially get another horizontal line, right? Whose slope would also be 0. So therefore, the marginal response would once again be equal to 0. Okay? Now you'll notice here that the marginal response is 0 at this point, and then after that it starts to increase, right? So our slope here would be a little steeper, our slope here would be even steeper, and then presumably as we got higher and higher and higher, the slope would just get steeper and steeper and steeper. So we say that on this portion of the curve here, there is an increasing marginal response, right? Increasing marginal response as we go in that direction. And of course, as we go down the purple curve that way, our slope gets less and less and less steep. So we have a diminishing marginal response on that point of the curve. Okay, these are all terms that you'll see later in your econ courses, the idea of increasing marginal response or decreasing marginal response. But I just thought I'd flag it here. Okay, so that's it for this video. Comment below if you have any suggestions for further videos. And if you find it useful, please share it with your friends and like and subscribe. Like the video, subscribe to the channel. I will see you in next